Okay, so this is going to be a revision session. We will revise a few important facts about perceptron, logistic regression, and SVM. So, in the context of perceptron, the most important fact that you need to sort of remember is the algorithm itself. So, first let us discuss this perceptron algorithm in full precision. Okay, so let us say you have a data set D, okay, which has data points xi, yi, I running from 1 to capital N. Capital N is the number of data points. What is xi? Xi is in some RD, which means there are D features. And what is yi? Yi is either +1 or -1. So we are using this +1 -1 notation for binary classification, right? Now the first step of the algorithm is where you initialize the weight vector W. Typically, the weight vector is initialized to the 0 vector. So typically W0 is chosen to be the 0 vector, but not always, okay? Not always. What do you do next? You maintain some kind of a counter. So let me call the counter C. So the initial value of the counter is just set to 1. Okay. Now in the third step, you run a while loop. So I hope everybody knows about while loops. So while C is bigger than 0, okay, strictly bigger than 0, what you do, first you initialize C to be 0, back to 0. Okay. And then you run over each and every data point. And when you run over each and every data point, what do? You check if yi, which is the true label of that data point, is equal to, or if it is not equal to, the sign function acting on W transpose X. So if the sign function is not equal to the true label, which means there is a misclassification happening. If there is a misclassification happening, then we simply update the value of W to be W plus YIXI. If it is being correctly classified, then there is no need of an update. Along with that, we also increment the value of C, which is C++. And this algorithm goes on. This entire step from step 4 to step 8, right? This is called an epoch. This is one epoch. Right? Similarly, this inside the for loop, this is one iteration. One iteration and one epoch. Okay. So specifically, you can see that the number of iterations, is same as the number of epochs multiplied with n. But in each iteration, it is not necessary that we will have an update. It may be updated, it may not be updated, depending on whether the misclassification is happening or not. So this is the entire algorithm of the perceptron. Okay. One more thing to note is that when you make an update, you don't go back to the first data point. You continue with the next data point. So let me make a note of that. After making an update, don't go back to the first data point. Continue with the next data point only. Data point. One more thing to observe is that the sign function, right? The sign function of any variable, let's say z, this is equal to +1 if z is bigger than or equal to 0, and -1 if z is strictly negative. One more important point about the perceptron is that if the perceptron algorithm converges after, let's say, k epochs, then it terminates after k plus 1 epochs. So let me write it down. If the perceptron algorithm converges after k epochs, what does that mean? That means that it terminates after k plus 1 epochs. So what is the difference? The difference is whether it converges or it terminates. So it converges early, right? But if you notice the algorithm carefully, you'll understand that there will be one more epoch which will be run, which will have no updates, and then we will understand that the algorithm has converged, and then we stop the algorithm. So when we stop the algorithm, it's called termination, right? So you're basically having one extra round, or one extra epoch with no updates. That is why it is terminating after k plus 1 epochs. One more important point I want to mention about perceptron is that it need not converge. Okay, before that, let me discuss the notion of linear separability. So we say that a data set is linearly separable if you can actually draw a line between the two class of data points. Linear separability. So let us say you have some data points here and some data points here. They are linearly separable, right? Because you can draw so many lines here. This can be drawn, this can be drawn. And all of these lines are separating the two class of data points. On the other hand, if you take, let's say, this kind of a data set, this is not linearly separable because whatever line you draw, you cannot separate the two class of labels or two class of data points. So this is not linearly separable. Not linearly separable. This is the intuition of linear separability, but what is the mathematical definition? The mathematical definition is that there exists some W star, okay, which is non-zero, such that yi times W star transpose xi is bigger than equal to gamma, which is strictly positive for every I. In fact, I should say there exists W star non-zero and gamma strictly positive such that this holds. What does this mean actually? See, yi times W star transpose xi, this is always going to be of the same sign. If it is the same sign, then it will be positive. Opposite sign, then it will be negative. So we are saying W star transpose is always classifying it correctly. And not just correctly, none of them is actually zero. What does that mean? That means there are no data points which are lying on the line. Every data point is either on one side of the line or on the other side of the line. There are no data points on the line. That is what this means. And this is the notion of linear separability. Why linear separability is important for us? Because in the perceptron algorithm context, if dataset is linearly separable, if dataset is linearly separable, then the perceptron algorithm will converge. Then the perceptron algorithm will converge. What do you mean by converge? Converge means it will land in some W. Okay, it will land in some W. It means it will reach some W which which classifies all data points correctly, right? At the same time, I should have written if and only if, because let me make that slight change. So the dataset is linearly separable if and only if perceptron algorithm will converge. Which so what I mean by if and only if is that if dataset is linearly separable, then perceptron algorithm will converge. And if it is not linearly separable, then it will never converge. That means it will go on running. Okay, that is what I mean by if and only if. Okay, I used this thing called gamma. What is gamma? So gamma is the you can think about gamma is as the distance of the closest data point to W star. So this is the distance of the closest data point to W star. See, saw W star, that is fine, but at the end of the perceptron algorithm, it is not necessary that we will end up in W star only. We can get some other W also. There is no uniqueness for this particular line, right? We can get some other line also. For example, as you saw in this example, there are two lines. Okay. One important point in the perceptron algorithm is the proof of mistake bound. So, mistake bound. What does it say? It says that you run the perceptron algorithm forever, right? If the dataset is linearly separable. So if dataset is linearly separable, right, then the number of mistakes that it can make, right? The number of mistakes that it can make is less than equal to r square by gamma square. Let's understand this properly. This is the number of mistakes it can make. What is the number of mistakes? Now let me go back to the algorithm. Whenever it does this, it is a mistake. So in the whole algorithm, okay, suppose you run it and then it runs for a long time and then it stops. Capital M represents how many times this condition has been satisfied, which means how many times yi is not equal to sign of W transpose x. And we see that it is upper bounded by r square by gamma square. What is r square? Gamma square we already discussed. What is r square? What is r? R is the distance of the farthest data point. R is the distance of the farthest data point. So in all of these cases, we are also assuming that our data set is centered, right? And that whatever line we are looking for is passing through the origin. So let me write that also. If data set is linearly separable and centered at origin. So basically we are looking for a line which passes through the origin. We are looking for a line which passes through origin. Again, this is a very weak assumption because the moment you have any data set, you can always add another uh, feature to it, a feature of all ones, right? In that case, you can think about uh, W as some weight vector with a bias, right? And then you can do the same thing. You can assume that it passes through the origin, right? Okay, but how did this? And there is one more important point that a lot of people miss is that this bound is satisfied only when, so only when W0 is the zero vector. If W0 is not the zero vector, then the mistake bound is not like this. The mistake bound is still there, but it is not like this. So what will be the mistake bound if it is not like this? So let us look at the proof. Okay. Suppose an update is happening. Okay. Suppose we are at some WT, right? And then we encounter a mistake. We encounter a mistake, and then we move to WT plus 1. What is the difference between WT plus 1 transpose W star and WT transpose W star? It is nothing but WT plus Y times X. So let us say the mistake happened on X comma Y. Then as per the update, WT plus 1 is equal to WT plus Y times X. So this can be written as this whole thing minus WT transpose W star. And that turns out to be Y times W star transpose X. Now we know that this is strictly bigger than or bigger than equal to gamma, which is strictly bigger than 0. Why? Because of the assumption of linear separability. Okay. Now let us say, suppose you finish t iterations. Suppose you finish t iterations. Let us say, okay, in total, in total. And in that t iterations, you are having m mistakes in total. Okay. M mistakes, or you can say m updates. Okay. Then the same thing, what I'm doing, I'm taking sum of t running from 1 to capital T, WT transpose W star minus WT minus 1 transpose W star. What will this be equal to? I don't know what this will be equal to, but this will be bigger than m times gamma, right? Because every time you make an update, it is either the same or it is, so whenever you compare between WT and WT minus 1, either they are the same if there has been no mistake, or there has been an update, which means the difference is at least gamma. And this updates have taken place m times, so it is at least bigger than m times gamma. But it doesn't end there. M times gamma minus W0 transpose W star. This is what it is bigger than. Again, now if you're assuming that W0 is 0, then you can say it is bigger than m times gamma, right? But what is this term? You can see that this actually cancels out, and what remains is W capital T transpose W star, right, minus W naught transpose W star, and that is bigger than m times gamma minus W0 transpose W star. What does that mean? That means that m times gamma is strictly less than WT transpose W star. This is our first important equation in the proof. Right? Now, by using Cauchy-Schwarz, you can say that this is strictly less than or even less than equal to, doesn't matter much, WT transpose or WT norm square, not norm square, just norm, in fact norm 2 times W star norm 2. Now, since we already have, what is our linear separability assumption? We are assuming that there exists a W star which is non-zero, which satisfies these criteria. We can at the same time, we can also assume that W star has norm 1. Because whatever W you give me, I will just divide by its norm and I will get a norm 1 vector, which is the same line, but its norm is reduced. And still I will be able to satisfy the same criteria. So having this assumption doesn't hurt. How it helps is because I can simply say that this is strictly less than equal to or less than or equal to WT norm 2. So here I have used Cauchy-Schwarz inequality, by the way. So Cauchy-Schwarz inequality, what does it say? It says that if you take x transpose y, that is less than or equal to norm of x times norm of y. That is what Cauchy-Schwarz says. Okay. So what is happening again? WT or WT plus 1 is equal to either WT if there is no mistake, right? And it will be equal to WT plus y times x if there is a mistake. This is the idea. Right? Now, so you can say WT plus 1 norm square. What can you say about this? This is equal to, see, if there is no mistake, then it will be same as norm of WT. But if there is a mistake, this will be equal to WT plus y times x norm square. And then it will be less than or equal to, using triangle inequality, WT norm square plus norm of x square. See, y is plus minus 1. So the mod is anyway going to be 1. So this is less than or equal to WT norm square plus R square, right? Because norm of x is bounded by R, right? That is what we said. R is the distance of the farthest data point. So finally, what we can say? We can say W capital T norm square is less than or equal to W naught square plus M times R square. Why M times? Because every time you are making an update, it is increasing by at most R square. So by the time you move from W0 to WT, it will have increased at most M times R square because M times updates is happening. This is the second most important inequality in the proof. The first important inequality we got. Right? Now let us combine both of them. So combining both of them, what can we say? We can say that M square gamma square, I'm taking the square of the first inequality, okay? M square gamma square is less than or equal to W capital T norm 2 square. And that is less than or equal to W naught square plus MR square. Now comes the assumption part. See, if you're assuming that W naught is equal to 0, then from here you can simply say that hey, M square gamma square is less than MR square. And then you can say that M is less than or equal to R square by gamma square. But what if W naught is not 0? Then what can we say? Then we can say that M square gamma square minus M times R square minus norm of W naught square is less than or equal to 0. When I divide by gamma square, I'll get M square minus M times R square by gamma square minus W naught norm square divided by gamma square less than or equal to 0. I can further write this as M square minus 2 times M times, I'm completing the square, okay, plus 1 by 4 times R to the power 4 by gamma to the power 4. Okay. This is my square, by the way. And then I have to do minus of norm W naught square by gamma square. And I also have to minus 1 by 4 R to the power 4 by gamma to the power 4. This is less than or equal to 0. So now, what does this mean? This means M minus 1 by 2 R square by gamma square a whole square is less than or equal to W naught norm square by gamma square plus, because it will come to the right hand side, plus 1 by 4 R to the power 4 by gamma to the power 4. Now what can I say? I can say M is less than or equal to half of r square by gamma square plus under root of norm of w naught square by gamma square plus 1/4 of r to the power 4 by gamma to the power 4. This is the mistake bound if you do not assume w naught square to be 0. Again, if you put w naught square 0 here, then you will get r square by gamma square. So this is the mistake bound. Mistake bound when w naught is not equal to 0. Okay, so that is more or less about the perceptron algorithm. Let us move to logistic regression. In logistic regression, the most important thing that one should know is the sigmoid function. What is the sigmoid function? It is a function from R to open interval 0, 1. And the function is given as sigma t equal to 1 by 1 plus e to the power minus t. This is same as e to the power t by 1 plus e to the power t. How does the function look like? Let us say this is my uh, y equal to 0, this is my y equal to 1. And this is my, let's say, t, which is the x-axis, or x-axis is t, and this is t equal to 0. The curve somewhat looks like this, the sigmoid function curve. And this point, where it is being equal to, where it corresponds to t equal to 0, this is nothing but y equal to half. And these are asymptotics. Asymptotics means they will never touch. They'll just get closer and closer, but they will never actually touch. You can easily note that sigma prime t, the first derivative, will be strictly positive, right? Which is why this is an increasing function. Increasing function. Secondly, you can notice that if t is positive, then sigma double prime t is negative. And if t is negative, then sigma double prime t is positive. Sigma double prime t is negative means what? It means it is concave. And when it is positive, it means it is convex. So it is not fully convex, it is not fully concave. When t is less than 0, it is convex. If t is more than 0, then it is concave. Again, this can also be easily shown. By taking the second derivative. One more thing I want to notice is that the sigmoid function is injective, is an injective function. What do I mean by an injective function? It means that if sigma t1 is same as sigma t2, then t1 will be same as t2. That is also obvious from the graph, right? If you draw a straight line which is horizontal, it will touch the curve only once. Exactly once it will touch, right? Wherever straight line you draw horizontal, it will touch the curve exactly once, which means it is injective. So in regression, what happens? In regression, we try to predict some y hat, which can be any real number, right? So typically it lies in minus infinity to infinity, which is nothing but the entire real line. In logistic regression, what we do is that we additionally map it using the sigmoid function to the open interval 0, 1. And we say that instead of y hat, what we are predicting is something called p hat. What is p hat? P hat is the probability that the class is equal to 1. This is the whole idea about logistic regression. And by the way, logistic regression is a regression. Okay, it is not. A lot of people say that it's not regression, it's classification. It's not like that. It is regression. It is being used for classification. That's all. Okay. So if this is the logistic regression, what is the loss function? Loss function for logistic regression. What is the loss function? The loss function is called binary cross entropy loss. Binary cross entropy loss. So the loss is measured between the true value y. Again, y can be either 0 or 1. So let me write it down here. So in logistic regression setup, the label y, the label y is either 0 or it is 1. The cross entropy is a function of y as well as p hat. And the function goes like this: minus y log p hat minus 1 minus y log 1 minus p hat. Again, you can easily check that uh, this will be high when y is 1 and p is very low, or y is 0 and p is very high. In these both cases, the loss function L will be very high, which is exactly what we want, right? So now this can also be written as minus y log of 1 by 1 plus e to the power minus w transpose x. What did I do? I just replaced p hat by this. Why did I do that? Because that is exactly what the sigmoid function is doing, right? Sigmoid function. That is all I applied here with w transpose x, because ultimately we are doing regression. Minus 1 minus y times log of 1 minus p hat, which will be 1 by 1 plus e to the power w transpose x. This turns out to be equal to y times log of 1 plus e to the power minus w transpose x. Again, I'm taking the reciprocal and I'm converting minus to plus. Same thing I'll do here. 1 minus y times log of 1 plus e to the power w transpose x. Okay, so this is the loss function. Now let us discuss the metrics that are being used in classification, especially in logistic regression. One metric is called the precision. So what is precision? Precision is nothing but true positive by true positive plus false positive. Again, I hope everybody knows what is true positive and false positive. So false positive means it is predicted positive, but actually negative, or actually zero, or actually negative. Okay. Positive means plus one, negative means zero. So that is false positive. Similarly, we have another metric recall, which is true positive upon true positive plus false negative. So what precision measures is that out of the ones which are being predicted positive, how many of them are actually positive? So the interpretation is this: out of the ones being predicted positive, how many are actually positive? Similarly, in recall, what is the idea? In recall, the idea is that out of the ones which are actually positive, how many of them are being predicted positive? Out of the ones which are actually positive, how many are being predicted or how many are being identified. Let us say you are working in some uh, fintech company and you want to raise alarms for fraud transactions. Okay. In that case, what do you want to be high? Precision or recall? You want the recall to be high. Precision low होने से चलेगा. It is okay if you are calling the customer and saying that hey, it is a fraud, but whereas it is not actually a fraud, that is fine. But recall should be high, which means the actual frauds should not be missed. Okay, fine. There is one more metric which is F1 score. F1 score is nothing but it is the harmonic mean of precision and recall. So it's like 2 times precision times recall divided by precision plus recall. And for every logistic regression problem, there is a threshold. The threshold is typically 0.5. Typically 0.5. But it can be some other threshold also. Let's say some capital T. Right? So what happens when threshold increases? When threshold increases, the false positives will reduce. When threshold increases, false positives will reduce, and therefore the precision will increase. Similarly, when threshold decreases, the false negatives, sorry, when threshold increases, the false negatives will increase, which means the recall will reduce. So this is the impact of the threshold on the precision and recall. Again, the other way around also can be said. When threshold decreases, false positive will increase, and then precision will decrease. Again, these are heuristics and not absolute. Or you can say that these are likely to happen. I'm not saying that it will always happen. Okay, it might not always happen. I'm just saying that it's likely to happen. Typically, this is being found in practice. And there is a reasoning for it. I think I've explained it in some other video. I think in that mock questions video, I've explained it. One more thing important about logistic regression is the decision boundary. The decision boundary of the logistic regression is still W transpose X equal to 0. Why? See, ultimately, what we are doing, we are predicting it to be 1 if P hat is bigger than 0.5 and 0 if it is less than 0.5. Right? So essentially, we are doing something like 1 by 1 plus e to the power minus W transpose X. Right? It's either bigger than 0.5 or equal to 0.5 or less than 0.5. And 0.5 is what? 0.5 is 1 by 1 plus e to the power minus 0. Now, using injectivity, what we can say? We can say that W transpose X, right, is bigger than, equal to, or less than 0. And this is the decision boundary. So basically, it has a linear decision boundary. Again, if somebody changes the threshold, still you will be able to do it. So let us say the new threshold is, uh, let us say it is 1 by 1 plus e to the power, let's say something like minus 2, right? Suppose this is the threshold. Suppose. In that case, what will be the decision boundary? The decision boundary will be W transpose X equal to 2, right? This is the usual decision boundary. Usual decision boundary. Okay, so that is all about logistic regression. Now let us move to SVM. So the idea about SVM is that, okay, so let's say you have some points here, okay, and let's say you have some other points here. What you do in SVM is that you draw a line in between them in such a way that if you draw these supporting hyperplanes, okay, if you draw these supporting hyperplanes, so let me name them, okay. The middle one is the separating hyperplane, and the ones in the side, they are the supporting hyperplanes. Again, the separating hyperplane will have equation W transpose x equal to 0. This will have equation W transpose x equal to 1. This will have equation W transpose x equal to minus 1. This distance is known as the margin. And the margin turns out to be 2 by norm of W. Okay, so what is the formulation for SVM? Formulation. There are various formulations, right? One is maximize with respect to W or gamma. Gamma, you have to maximize gamma such that yi times W transpose xi bigger than equal to gamma for every I, and norm of W square is equal to 1. Again, this is very important. If you don't have norm of W square equal to 1, then gamma can be as large as possible. Okay. But now it turns out that we have W also, gamma also, and it's very hectic. So we get rid of gamma and we say that just maximize with respect to W. Instead of gamma, is just write 2 by norm of W, just the margin, such that yi times W transpose xi is bigger than equal to 1 for every I. Why 1? See, you can take any number, but 1 is very comfortable. That is the only reason we have taken 1. You can actually take any number. And in that case, let's say you are taking k. Suppose you are taking k. In that case, the supporting hyperplanes will be W transpose x equal to k and W transpose x equal to minus k. Just remember that. Again, maximizing this is same as minimizing norm of W square by 2. Okay? I'm just adding a square. Just like. So this is my hard margin formulation. Two formulations are there, and the setup. Again, this works only if, so this is for hard margin, by the way, hard margin. And when does this work? This only works when data is linearly separable. If the data is not linearly separable, then this does not work. In that case, we'll have to go to soft margin SVM. So in soft margin SVM, what we have, let's say I have this kind of a data set, right? Okay. This would be the hard margin setup. But in soft margin setup, we can have other possibilities. For example, I might have a data point here. Okay. I might have a data point here, and I might also have a data point here. There are three cases, right? So what is this case? This is the case when it is correctly classified, but it is inside the margin. Correctly classified, but inside the margin. What is this case? This is when incorrectly classified, and outside the margin. This is when it is incorrectly classified and it is inside the margin. So there are three cases that can arise. So all of these three are outliers, by the way. All of these three are outliers. This is an outlier, this is an outlier, this is an outlier. But what is the mathematical formulation for this? Formulation of soft margin SVM. What is it? See, most of it is the same. We'll be minimizing with respect to W, norm of W square by 2. See, initially we had norm of W square by 2. Okay. Such that, see now instead of yi times W transpose xi being equal to bigger than equal to 1, we say something else. What is the yi times W transpose xi for all these points? So let us say again, let me say this is W transpose xi equal to 1, not xi. W transpose x equal to 0. This is W transpose x equal to 1. And this is W transpose x equal to minus 1. In that case, for this point, let me name the data points. So let us say this is x1. Okay? Or yeah, this is x1. And let us say this is x2. This is x3. So what will be W transpose x1 times y1? It will be this distance. So let me write it down. W transpose x1 times y1. It will be something which is bigger than 1, right? In fact, it will be bigger than 2 also, by the way. Say, let's say something like 3. Okay. No, this will be bigger than 2. Yeah, it can be 3. Okay, it can be 3. Again, what will be W transpose x2 times y2? So y2 times W transpose x2, that will be this distance, right? And that is bigger than 1, right? And it will be, let's say, okay, it will not be, it will be something like minus 0.5, right? Minus, minus 0.5. Let me not write 3 instead of 3, let me write 2 because it's not that far away. Okay, it is incorrectly classified, so it has to be minus 2, sorry, minus 2. What about x3? See, W transpose x3 is what? It is, let us say, negative 0.5, okay, not negative 0.5. Yeah, let's take negative 0.5, okay. But y3 is negative, so negative negative will become positive and this will be 0.5. These are the three cases that we have. And in all cases, you can see that all of these are less than 1. All of these are less than 1. And therefore, what we do, the modification is that we write, instead of yi times W transpose xi bigger than or equal to 1, we write 1 minus eta I or zeta I. And these zeta I, we want them to be bigger than or equal to 0. We don't want them to be negative. But what are these zeta I's? These zeta I's are actually not desirable. These are undesirable quantities. We want it to be as small as possible. They're called slack or penalty. But they are undesirable. Undesirable. We don't want outliers in our model, right? And these are all outliers. Therefore, what we do is that we try to minimize the average outliers that we get. That is the only difference. Okay, what is C? I introduced a new character C. What is C? C is a hyperparameter. Hyperparameter. And what is the effect of C? If C is increasing, then zeta i's should decrease. That means there will be lesser mistakes. What does that mean? That means that the margin will be small. Lesser mistakes means what? The margin will be smaller. Right? And if you want more mistakes, or if you want a big margin, if you want a big margin, then what do you need? You need more mistakes. More mistakes means zeta I is high. That means C is 2. Okay, what if C is infinity or very high? Then we have the condition of hard margin SVM. Because then, if C is very high, if C is very high, then eta I or zeta I has to be 0. Because zeta I has to be equal to 0. What if C is 0? If C is 0, then the optimal W that you get, that will be the 0 vector. And this is not desirable. This is also an undesirable criteria. Usually we never use C equal to 0. Observe one important thing about these zeta i's. Observe that zeta I is bigger than equal to 0 and zeta I is bigger than equal to 1 minus yi times W transpose xi. So from here we can say that zeta I is bigger than equal to max of 0 comma 1 minus yi times W transpose xi. And as per the objective function, we want zeta is to be as small as possible. What does that mean? That means zeta I is equal to max of 0 comma 1 minus yi times W transpose xi. Why equal to? Because we want zeta is to be as small as possible. Look at the objective function. We want to minimize some average of zeta is. So zeta is will be as low as possible. Therefore, it will be equal to this particular value all the time. So I can rewrite our optimization problem as minimize with respect to W norm of W square by 2 plus C times 1 by N of summation of max of 0 comma 1 minus yi W transpose xi. What is this? This is known as the hinge loss. The hinge loss is given to be LT is equal to max of 1 minus t. Sorry, max of 1 minus t comma 0. Again, this is a convex function and it is not differentiable. Again, this is sometimes thought of as the regularization term. So see, this is same as that of regression, right? In regression, we had the square loss plus regularization. In SVM, we have the hinge loss plus regularization. One more important thing about SVM is the dual SVM, right? So general dual principles are there are a lot. We will discuss some of them. The idea is this: suppose you want to minimize some function f of w, right, subject to some criteria, let's say gi w less than equal to 0. There are so many constraints. That's why I'm taking gi, right? Let's say I running from 1 to little n. Okay, there are n constraints. Then this can be written as minimize with respect to w, maximize with respect to some parameter, let's say lambda I non-negative, fw plus summation of lambda I giw, I running from 1 to n. These are the same problem. Okay, why these are the same? That also I have explained in another video. You can please watch it. Now, one thing I want to mention is that when okay, so let us say I want to swap the min and the max. Let us say I'm considering min of okay, this is for any function. Okay, min of with respect to w, max with respect to lambda. Let's say you have some function h of w comma lambda. Suppose this will always be, or you can suppose my objective is to compare this with max with respect to lambda min with respect to w, h of w comma lambda. It always turns out that the left hand side is less than equal to this. Why, I will probably explain in some other video. This is the revision video, I don't want to get into it. But this always holds. Always holds. But when H is convex, then they are equal. This is the whole idea about duality. And this is called strong dual or strong duality theorem. And this is called weak duality theorem. Weak duality theorem. Why it is beneficial for us? Because, see, what is our dual? Our dual will be max with respect to alpha I non-negative and beta I non-negative, min with respect to w and zetas, norm w square by 2 plus c times 1 by n summation zeta I plus summation alpha I times 1 minus yi w transpose xi minus zeta I plus summation beta I times minus zeta I. Please go back to these equations and see why this is the case. It's very easy. Instead of lambda i's, I have taken alpha i's and beta i's. That's all. I can take or consider this entire thing as L with which is a function of W, zeta, alpha, and beta. Now, if I take the derivative of L with respect to W and set it equal to 0, I will get W to be a function of alpha and beta, and that will be equal to summation of alpha I xi yi, which can also be written as x y alpha. What is my x? X is the matrix of data points, x1 up to xn. What is my y? Y is again a diagonal matrix where the labels are provided in the diagonal and the other entries are 0. And alpha I is nothing but a vector of alpha 1 up to alpha I. Remember, there are how many alphas? N alphas. Each alpha corresponds to a constraint. It's very crucial. And the moment I take the derivative with respect to zeta I and set it equal to 0, I get that alpha I plus beta I should be equal to C. So most of the time what happens is that we don't use beta I, we just use alpha I because beta is always C minus alpha I. What you can do, now you can plug in W or W star alpha comma beta into L of W, zeta, alpha and beta, and you can get this maximize with respect to alpha and beta, or maybe just with respect to alpha, which is non-negative, alpha transpose vector of all ones minus half of xy alpha transpose xy alpha. Such that, what is the criteria? The criteria is that 0 less than equal to alpha less than equal to c, or you can say alpha I less than equal to c for every I. One thing I want to notice here is that if you observe this carefully, this is nothing but alpha transpose y transpose x y alpha, and you can notice x transpose x here. This helps us to introduce kernel SVM. Whenever there is an x transpose x, you have to replace it by phi x transpose phi x, right? And that is nothing but the kernel matrix. Again, you can observe that when c is 0, when the value of c is 0, then what happens? Then alpha has to be 0, right? And in that case, W star will be equal to xy alpha, which is equal to 0. Again, when c is infinity, then It is a case of hard margin. One more important concept in SVM is that of complementary slackness. Again, this is a topic in optimization. If anybody is interested, I can make an entire 1 or 2 hour video on complementary slackness. If anybody is interested, let me know in the comments. This is a big topic in optimization itself. For SVM, there are two CS or complementary slackness theorem, CS1 and CS2. CS1 says that alpha I star times 1 minus yi w transpose or w star transpose xi minus zeta I star is equal to 0. CS2 says that beta I star times minus zeta I star is equal to 0. What is happening here? I mean, from where does this come? Observe carefully that these are the dual variables and these are the primal constraints. So basically what complementary slackness says is that the product should be 0. One of them should be 0. Both of them cannot be positive or both of them cannot be strictly negative or strictly positive. That is the whole idea. Okay. From here, this actually helps us to determine the behavior of data points. Behavior of data points using the dual variables alpha I or alpha I star. Actually, the optimal value. So these are for this. This is for the optimal value. For optimal alphas or alpha stars, beta stars, and W stars. Okay, not for any arbitrary alpha, beta, or W. Only for the optimal ones this will hold. Okay, what happens if alpha is 0? If alpha is 0, then beta I has to be strictly positive. And that immediately says that zeta I has to be 0. Again, I'm not writing the star every time, okay, but this is for optimal. So let me write it for optimal alphas, betas, and Ws. And zeta I is always bigger than equal to 1 minus yi w transpose xi. What does that mean? That means yi times w transpose xi is bigger than equal to 1. What does that mean? That means it is correctly classified, and it is outside the margin. What if alpha I lies between 0 and c? In that case, beta I should also lie between 0 and c. And then zeta I has to be 0. Again, I can say that 1 minus yi times w transpose xi minus zeta I has to be equal to 0. Again, zeta is already 0, so this will get cancelled out. And you can say that 1 minus yi times w transpose xi is equal to 0, which means it is correctly classified and it is on the margin. Why on the margin? Because yi times w transpose xi is equal to 1. That means it is on the margin, right? There is one more case, which is when alpha is equal to c. When it is equal to c, then beta I has to be equal to 0. You cannot say anything about zeta I. The only thing you can say is that 1 minus yi times w transpose xi minus zeta I has to be 0 because of CS1, due to CS1. Now this means that zeta I is equal to 1 minus yi times w transpose xi, which is obviously bigger than equal to 0. So what does this mean? This means yi times w transpose xi is less than equal to 1. This has a lot of interpretations if you observe carefully. It can mean on the margin. It can also mean within the margin and classified correctly. plus correct classification. It can mean within margin plus incorrect classification. It can also mean outside margin plus incorrect classification. All the four possibilities are there. Okay. Okay, that is more or less all about the revision from all the way from perceptron, then logistic regression, and then SVM.